Hello and welcome to section 5, Gibbs sampling. The motivating example here is how to obtain samples from the posterior distribution given that the person does not wear a mask and has difficulty breathing. So P of X, like all the remaining variables except for M0 and B1. We already saw how to do this if this was a particular event, and some of the methods may actually generalize to a joint distribution of X conditioned on some evidence. Here we want to see how to do this by using Gibbs sampling, the so-called Gibbs sampling method. And I thought it's easier to explain it by first an example. So we will go through this and then we will formally present the algorithm itself. So if I want to do this using Gibbs sampling, first note that I have already an evidence Z equal to M0 and B1, and this will simplify some of the CPDs. Okay. We have a set of reduced factors. So we saw this in the exact inference section. So P of M, for example, will be now P of M0, 1 over 3, and so on. Some of the other ones based on the evidence will be simplified. Now, P phi of X, this is how we define it, is P of X condition on Z or P of X condition on M0 and B1. Okay. This is just the notation. So here's what we do. So again, like you see that the CPDs are simplified by crossing those values that will never appear based on the evidence. So first we generate a particle, a first particle by any method. For example, forward sampling. We need one first particle for Gibbs sampling. And imagine that we have done this. So here we have a total of 6 variables. 2 of them are determined. The other 4 are here. And imagine after doing that, you will get these ones. So C1 for COVID, F0 for fever, and so on. So I have this iteration 0, or perhaps I should, iteration 0, particle 0 values. And if I put them together with the evidence, this is what I will get. Great. Now, use some ordering. Unlike forward sampling, which needed a topological ordering, here you can use an arbitrary ordering. So here, for example, we go with CFVD. And then we do the following. So we have the observed ones. We have the first particle. First iteration, we start as follows. We should go through each of the variables according to the order, which is the same as what we have here, CFVD. First iteration, first variable, which is C here. So we need to sample C1. This was iteration 0. I need iteration 1 using the reduced CPDs. And that is basically getting probability of C condition on the other ones, F0, V0, and D1. Okay, these are basically the values I have from my first particle. And of course, this should be really together with M0 and B1 because they are also observed. But this is just a compact notation of P phi, so it's implicitly there. So by definition, this will be P of phi of all of them divided by P phi of these 3 variables here. Okay, so if I do that, again, I can marginalize some variables out. The point, though, is that here, in the nominator, I don't need to marginalize anything. Everything is actually given. The only thing that I want to sample from is C. Right? P of C. Everything else, I mean, M0 and B1, they are the evidence, they are given. The other ones, we also assume that they are given. Why? Because we're using the information from the previous particle. So I will replace literally every other F, V, and D with what I saw from what I got from the first particle 0. Okay? Which was obtained from forward sampling, for example. So the factorization I have here of the whole joint distribution, and the same appears in the denominator, just that I need to sum it over the possible values of C here. So we'll get this form for the nominator, I cannot cancel out the C values. And same with the denominator, some of them will just cancel out. So for example, PM0, these two cancel out, right? PD1, same here, and also this one. So it will be reduced to this. And then by inserting the values of the reduced CPDs, if I replace them, I will get that the conditional CPD for, or this probability for C is as follows. It's just impossible to get the value C1, it's C0, and you will always get C1. So okay, if I update or if I resample C, which was the first variable, I have to get C1 in this case. This is the extreme case. Of course, we almost always will have a number between 0 and 1. Okay, so what happened so far? I had an initial particle from forward sampling, and then I said, now I want to update the value of C1. This is where really Gibbs starts. I updated, in this case, it appeared to be the same value as in the previous iteration. Okay, so, and you see that it's based on all of these values. Now, I want to update the second value, the second variable, F. Remember that we had an ordering, CFVD. The second one was F. Now, the distinguishing point here is that compared to, for example, forward sampling or likelihood weighting, is that now when I want to sample F, I won't go back to C0. I will I will rely on C1, the updated version of C. In this case, they are the same, of course, but we will see that they can easily be different. So first iteration, second variable, sample F1 from the corresponding the probability distribution F conditioned on C1. If we do this, this is what we see. So it's P phi F condition on all of the other variables, C1, V0, D1. And if I write down the distribution, we see that everything cancels out except for P of F condition on C1. And this is basically coming from the network itself. If you don't want to write all of that down each time, this is what you can do. So here, for example, for COVID, we had that it has its parents, but it also has 2 children. That's why in the probability distribution, it appeared 3 CPDs appeared when we wanted to update its value. 1 for the parents and 2 for each of the 2 for the children, 1 for each child. But for fever, it doesn't have any children, it only has a parent. That's why only P of F condition on C appears. Okay, here it is. Okay, so if we simplify it, we will get this value, and we can see if we look at the CPD, we will get 0.1 and 0.9, and either of them can happen when we update F. Most likely it will be F1. Okay, so we get this. Now, a summary of what happened so far. I updated C1. When I was updating F1, I used all of V0, D1, M0, B1, but not the original value of C1. I used this new one. Well, in this case, again, they were the same, but it won't be the same with V1. When I want to update V1, I shouldn't use F0. I should use the new value F1 here. So let's see. First iteration, third and fourth variables. So how we do this, for V, it will be V condition on B1. Also, V doesn't have any children, so it's only this term. And what we see is that we will have 0, 1, 0.1, 0.9. And if I update, for example, this one will happen. It's not necessarily the greater one. With some probability, this will happen. So as we see, for updating V0, we used the updated value of F1 and the updated value of C1. So what about D1? Well, same story. For D, we will update it. Here we have P of D. It has, it doesn't have any children, any parents, right? Social distancing, but it has a child, C. So this is what appears for the updating the conditional probability distribution, and this is what appears for the values. So we can sample that and we will get, for example, D0. Okay, so this is the result of the first iteration. Now look again, D0 is based on the updated value of V and F and C. M and B, they're just observed and they don't get updated. So we get the second particle, which is, I just listed all the updated values of the variables. Now, that is just one particle. But if I want to get a second particle, then I need to redo things, but I will start not from the initial particle that was obtained from forward sampling. I will do it based on this last particle. So again, I will start with the first variable, C2, but then this one is obtained similar to the previous case. It's just based on these three CPDs, and I will update the values. I will get these conditional probability distributions. If I insert the values from the CPDs, this is what I will get, and then I can update and get, for example, C1 or C0. So I'm using these updated values. You see I'm using all of the updated values from the previous particle here, and then that's how I update C0. And the same story goes with the other ones. So I can do the same for F1, V0, D0, and I will get the whole new particle, and then this will be the idea for, it will be the basis for the third iteration and so on. Okay, so that was to see it in an example. In general, the Gibbs sampling is as follows. When we want to calculate we want to generate a Gibbs chain sequence x0 to xt for this posterior p of x condition on z. So we have a set of variables to be sampled. Note again that there's no ordering here. It's just a set of variables. Z is the set of observed variables. T is the total number of iterations. And step 1 is to reduce the set of factors in P given the observed value Z to get the set of factors. So we simplify the CPDs. Set initial values x0 to all unobserved variables x. This can be done by forward sampling, for example. And then for iterations T from 1 to capital T, do the following. So we set the initial value of the new particle based on the previous particle, and then we update the variables in any order, arbitrary order. We sample xit from the factors, the simplified factors. This is just to say that you need to simplify the factors. But the key is here, and assign the new value to it. So meaning that each time you update one, you need to update the value of xi, and for the next variable xi plus 1, you will use that updated variable value for the previous variable. The algorithm goes from one node to another, so information flows across the network. And particle x0 can be generated by using, for example, the mutilated network and forward sampling. Either way is fine. And in an iteration, each unobserved variable gets a new value given the most recent values of all the other variables. We talked about that. For a Bayesian network with evidence, p phi of x is basically px condition on z. So these are just the those were just the notations. And to summarize, how can we generate based on the Gibbs sampling? This is the Bayesian network. We get the initial setting the initial particle from some method, and then we update the variables one by one based on some order. We get the first iteration, redo that based on these values that we get, the updated values. We put them in, they will form our first particle, and then we go to the second iteration and so on. Okay, now note this is time step or step at how it flows. So we really need to first do the first iteration, then do the second iteration, and so on. And inside the first iteration, we first need to do C1, then F1, then F, then V, then D. They cannot be done in parallel. Okay. So does the algorithm converge to the posterior distribution, or how long does it take? Does it? And if yes, how long? And this is the topic for the next section. Thanks for your attention.